Unit 11 notes part 4 just reaffirms the hydrolysis part, which are just the equations that we're used to. If you look at the two equations that are up top, the one on the left, the NH4 plus water gives you NH3 plus hydronium. That is an acid. You see NH4 lose an H from left to right. On the right, you see CN minus gain an H from left to right, and that would be the general form of the base equation. When we add an acid and base together, we are trying to get neutralization. However, that doesn't always occur. In the case that you add a strong acid and a strong base, you get a neutral salt and water. If you add a strong base to a weak acid, your final solution is going to be basic. If you add a strong acid and a weak base together, it's going to end up acidic. And if it's a weak acid and weak base, you're going to have to look up the Ka and Kb values to determine whether it's going to be acidic or basic. Usually the only time you'd see that is in a free response portion of an AP test, where you'd solve for Ka and Kb and then compare and decide if it would be acidic or basic. The type of questions that you're normally going to see look like these down here. Determine whether these salts are acidic, basic, or neutral. And here's how you do this. Every compound has two parts, the positive cation, the negative anion. So in this case we have K plus and Cl minus. Acids and bases have two parts. You have OH minus and H plus. So what we're saying when we see KCl is that it's really made up of KOH and HCl being added together. So we're trying to decide if that's acidic, basic, or neutral. Well, any element from the first column, so that would be potassium, anything from the first column plus strontium, calcium, and barium, when they're with hydroxide, is a strong base. So anything from the first column, strontium, calcium, barium. So in this case, this is a strong base. For your purposes, you need to know three strong acids. You need to know HCl, H2SO4, and HNO3. So HCl obviously is one of those and is a strong acid. So this is a strong base and a strong acid. So KCl as a salt solution would be neutral, meaning it was formed from a strong acid and a strong base reacting together. NaF would be NaOH, because the first thing always goes with OH, and then HF. HF is not one of the strong acids listed above. NaOH is a strong base because Na is in column 1. So this is a strong base and a weak acid. So this would be basic. Same thing here. You would have zinc hydroxide and nitric acid, HNO3. HNO3 is a strong acid. Zinc is not in the first column. It is not strontium, calcium, or barium. So it is not a strong base. It's a weak base. So in this case, it would be acidic. And D is an example of the weak base and weak acid where you look up the Ka and Kb values. This one actually ends up being basic. We're not going to worry too much about that situation. We'll do some more examples with it as we get closer to the AP test. So then, just as H3O plus, concentration of H3O plus times OH minus always equals 1 times 10 to the negative 14th. So too does Ka times Kb always equal Kw, which is 1 times 10 to the negative 14th. The reason why this occurs is if something is an acid, its conjugate base would be the opposite of it. So in this case, we want to calculate Kb for F minus, and we're given Ka. So notice how F minus and HF are differ by 1 H. Okay, so in an equilibrium equation, this would be on the left, let's say, and this would be on the right, or vice versa. So if one value is high, the other one has to be low, since they work as a pair together. So to plug in, you would just do Ka 6.8 times 10 to the negative 4th times Kb equals Kw, which is 1 times 10 to the negative 14th, and you'd solve for Kb, and you would get 1.47 times 10 to the negative 11th. Now, realistically, you're not going to see a bunch of those where you have to plug in and just do that one step. It's going to be buried into a bigger question. So that's something like here. What is the concentration of benzoic acid in an aqueous solution that's 0.015 molar sodium benzoate? Now, it gives you sodium benzoate and wants benzoic acid. The way you recognize an acid is it always has an H in front, or in this case it told you it's benzoic acid. But then it gives you a concentration of sodium benzoate. Sodium is always soluble in water, meaning it's not going to be any part of the reaction. So what we're worried about then is the benzoate ion. So benzoate is a base, and I know it's a base because it doesn't have hydrogen in the front. Anytime you see any compound given to you and hydrogen is not the first element, assume it's a base. So it's a base plus water, and it's going to give you Hb plus, which in this case is going to be benzoic acid, because benzoic acid would have gained an H from benzoate, and OH minus. So when we do our ice chart, like we normally would, this is 0.015 to start with, because sodium benzoate, the benzoate ion, would be 0.015. This would be 0, 0. So minus x, 0.015, minus x, 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 x. Now, we're using a base equation, but we're given Ka. So you're going to have to solve for Kb, because we need it because we have a base equation. So Ka times Kb equals 1 times 10 to the negative 14th. Plug in 6.3 times 10 to the negative 5th. I'm going to assume you guys can plug it in and divide 1 times 10 to the negative 14th by that number. And solve for Kb, and it's 1.58 times 10 to the negative 10th. Now we can plug into our equation because we're looking for the concentration of benzoic acid, which is x. So our products, x times x, or x squared, over our reactants, 0.015 minus x, equals 1.58 times 10 to the negative 10th. Now if you remember from part 3, if 0.015, our concentration of our acid, or a base in this case, is greater than, divided by our Ka or Kb value is greater than 100, we can get rid of this. And 0.015 divided by 1.58 times 10 to the negative 10th is definitely bigger than 100. So I can get rid of that. I'm going to solve for x, and it's 1.54 times 10 to the negative 6th. That's the concentration of Hb plus, which is in this case is benzoic acid, and it's also OH minus. The second question asks, what's the pH? Well, what I'm going to do is I'm going to use the fact that I know the concentration of OH to my advantage, because I know pOH is negative log of OH. So the negative log of 1.54 times 10 to the negative 6th is going to be equal to my pOH, which is 5.81. I know that 14 equals the pH plus the pOH. So if I plug in 5.81 as my pOH and solve for pH, pH ends up being 8.19. On the back side, we're going to have to deal with common ions. And all a common ion says is that equilibrium is going to shift if you add something that is common. So in this case, the best way to do it is look at an example. It says with the addition of HCl. Well, HCl, when you put it in water, forms this, H and Cl, and H when it's in water is H3O+. So basically what it's saying is I have this equilibrium right here. I'm adding HCl, which does not add acetic acid, it doesn't add water, it doesn't add the acetate ion. All it adds is that. So if you're adding something to the right, equilibrium has to shift left. The second question says, what will happen to the degree of ionization? Well, if you're shifting to the left, it means you're taking this ion that broke apart from acetic acid and you're making less of it because you're shifting to the left. So the degree of ionization will decrease because it's not breaking apart as much as you shift back to the left. The final example, we're just going to pick one of the two down here just to show you how the common ion effect would work in an ice chart problem. It says, what is the concentration of formate ion in a solution that is 0.1 molar formic acid and 0.20 molar HCl? And it gives you Ka. So I know that I have formic acid, the HCHO2. I know it's an acid because it starts with H. So I'm going to take the general form of the acid equation to start this. And I'm going to go with an ice chart. Now it tells me that originally my acid is 0.1. It also tells me I have a 0.2 molar HCl. Remember, HCl is a strong acid that completely breaks apart into two things, H and Cl. And in this case, H is H3O+. So I add 0.2 to begin with here. I have 0 of this still. Then the ice chart just fills in just like how it normally would. Minus X, plus X, X, X. I know what Ka is, so Ka is 1.7 times 10 to the negative 4th equals X times 0.2 plus X over 0.1 minus X. Now remember, if the initial concentration of my acid, 0.1, divided by Ka, 1.7 times 10 to the negative fourth, is greater than 100, which in this case it is, we can get rid of the positive, or plus x, and the minus x. So that's going to make solving for x a lot easier. In this case, x ends up being 8.5 times 10 to the negative fifth. The second part then says, what's the degree of ionization? Degree of ionization, again, is just your x, your change value, 8.5 times 10 to the negative fifth, divided by your initial value of your acid, 0.1. So it's 8.5 times 10 to the negative fourth, or 0.085%. So not a lot of breaking apart in this problem.